Okay, good morning, friends, and welcome back to the next lecture on heat transfer. Yeah, today is what, 3rd of November, so we are slowly coming towards the end of this semester. And I know today is the week, today is the day just before the Diwali weekend. But we have to go, we have to move on, we have to complete the syllabus. So we will continue from where we left off in the last class, which was natural convection. Right, we had just started natural convection. We discussed what natural convection is. We got introduced to the two new non-dimensional terms. One is called the Grashof number. The other is called the Rayleigh number. Grashof number, as we like Reynolds number, the corresponding counterpart in force convection is Reynolds number. Reynolds number was the inertial force over viscous forces, or a measure of the inertial forces over the viscous forces. Grashof, similarly, is the buoyancy forces over viscous forces, because it's a buoyancy force that pushes the fluid up, right? That leads to the flow motion, the fluid motion. Okay, but it's the viscous forces like before, which would like to pull the fluid back because of the shear forces at the wall. So these are the two opposing forces, and depending on which one is dominant, that will determine how strong your natural convection is going to be. Okay. And at the end, we talked about mixed convection, which is when, natural convection means that there is no bulk movement of the air. The only movement is because of this density difference resulting in the buoyancy forces. But however, in most practical situations, there will be some movement of the air. I mean, you cannot help it. For example, in this room, just by leaving the two windows open on two sides, there will be some air current. You cannot help it. Okay. Even when I'm not putting on the fan. Every time somebody opens the doors, there will be a pressure difference and there will be some pressure driven flow. Okay. Someone walks into this room, even the way we breathe, there will be some air movement. Okay. And there will be situations when this air movement is significant enough so that its effect on heat transfer cannot be neglected. Okay. So in such a case, we call it mixed convection, where it's the effect of both natural and forced convection. Okay. And the effects are comparable. And how do we determine if their effects are comparable? We say that the measure of Grashof over Reynolds to the Reynolds squared. Actually, there's a number called Richardson number. If that ratio is about 1, it means that it is mixed convection. If it is much greater than 1, it means it's natural convection. If it's much less than 1, it means forced convection. Okay, so let me start sharing my screen, which this is where we left off in the last class. Okay. Oops, what happened? Oh, okay. All right, so this is where we talked about. So pure natural convection will be when this ratio is much greater than 1. So Grashof is the dominant. The buoyancy forces are dominant over inertial forces. Forced convection is the inertial forces which dominate the buoyancy forces. Okay, so now let us, with that introduction in the last class and basically the fundamental concepts, let us move on to some particular cases, and the most important is a vertical plate. Okay, so I have a vertical plate which is at a high temperature. Okay, as I said, in natural convection, we always have to spell out the direction of gravity. Okay, now as before, I'll call this direction as x and this direction as y. Okay, so now at any point of time, what we discussed last time is, okay, and before that, sorry, this temperature is TW and away it is T infinity. Okay, and of course TW is greater than T infinity. Okay, so what we discussed last time is that the air right next to the heated wall is going to heat up, as a result of which its density will come down, it becomes lighter, and therefore it will be pushed by buoyancy forces to move up. Okay, now what happens? Now we know, let me draw this line. Now the velocity at the wall has to be zero because it's a no slip boundary condition. So it is zero. As we move out, because of the buoyancy forces, we will have a certain finite velocity, and therefore the velocity increases. Okay, so the velocity in the x direction increases. Okay, so let me write that down. Velocity at wall, which is y equal to 0, is 0. Okay, at slight distance away from wall, u increases. Okay, with further increase in y, actually u decays. Why? Because my delta t and as a result the buoyant forces reduce. Okay, let's also note that the temperature is going to reduce from TW at the wall to T infinity at a certain distance away, right? So let me draw that as well, like this. Okay, so somewhere it becomes T infinity. This is how the temperature changes. So let me write that also. Temperature okay. Now, because this reduces, what happens is that the velocity will also reduce. What happens over here when the temperature of the air is at the ambient temperature? There is no buoyant force and therefore no velocity as well. So therefore, unlike forced convection, where the velocity changes from 0 to a maximum value, here the behavior is somewhat different. What happens is it increases and then it falls again and reaches a value of 0. Okay. So please note one thing. That's before, let me complete this and write that eventually u becomes 0 as t approaches t infinity. Okay. So please note there is a single boundary layer. Okay, which is a natural convection boundary layer. Okay, it's a single boundary layer. It's not like velocity reaches its mean free stream value earlier than the temperature reaches and all that. When the temperature comes down to infinity, velocity comes down to 0. So this is going to be my single boundary layer of thickness delta, which is going to vary as a function of x. Okay, so please keep that in mind. This is a major difference from forced convection. That over here, I would say corresponding, there is no concept of velocity boundary layer. Okay, there is one boundary layer which is essentially the temperature boundary layer, and within that the velocity changes from 0, rises to a maximum value, and again comes down to 0. Okay, all right. Now if I look at it from a distance at a macro scale, what happens to this delta? Okay, so if I look at it from a zoomed out view, what happens is this boundary layer again, like before, increases from the leading edge. Okay, so this is my delta x, or delta is a function of x. So what happens here? I'll have something like this, right? Again here, something like this, and so on. Okay, also here, something like that. So this is how the boundary layer grows. And similarly, I will also have the thermal boundary layer all the time. Okay, so I can write that the boundary layer grows from the bottom edge as x increases, right? And at any value of x, we have a velocity and temperature profile. Clear? Let me erase this because it is making it a little cluttered, but you understand what I'm trying to say. These two, I think, is good enough to show that how it increases. Okay. All right. So what people have done, we are not going to derive any equations or anything here. I'll just give you the values. Delta x is actually 5x Grashof x by 4 to the power minus 1 by 4. So which means, okay, so the delta x grows like this. So delta x over x is what? 5 times Grashof to the power minus 1/4 by 4. Okay, now we had root over Reynolds number to the power minus half for force convection. Okay. Then what is the proportionality to x? For force convection, it was parabolic. Remember, delta was proportional to x to the power half, right? So in natural convection, what is the dependence? Can somebody tell me? Work out and tell me. Anyone? Come on, this is easy.
So power 1 by 4.
Yes, correct. It's the power 1 by 4. Why? Because x Grashof is x cubed. So this would be x to the power minus 3/4, and this is x. So to the power 1/4. So again, let me just put a name here. I put a blurb here. Remember, in forced convection over a flat plate, delta was proportional to x to the power minus half. Sorry, yeah. X to the power half, sorry. Okay. So there the growth was faster at a higher rate than in natural convection. Secondly, remember, also note that this delta x depends on delta t because Grashof has g beta delta t. Okay. All right. So now what I will do is I will move to some PowerPoint slides. Okay. So from here you can make a note that refer to slides. So I'm just showing you what I have in the slides. This is actually a pretty elementary one, but this is all we have discussed. So Grashof number we know, Rayleigh number we know. We have discussed all this. We have also talked about mixed convection. Okay, and now we are considering vertical plates. This also we have done. There's a quiescent fluid. gravity acting downwards, and you can see that there's a boundary layer, and within that the velocity profile looks something like this. So till now we have done this here. So this also we have done before. So this is your x momentum equation, this is your energy equation, and as before you can see that you have temperature in the momentum equation, you have velocity in the energy equation. So these equations are coupled. It's not easy to solve. Okay. So derivation is out of it's something called similarity solution, but it's out of scope for this class. We are not going to do it. So now let us look into where we just stopped here. The Nusselt number, okay, it can be shown if you do these analytical solutions or even similarity solutions, it can be shown that the Nusselt number correlation looks something like this. Okay, it is Grashof by 4 to the power 1/4, okay, times a function of Prandtl number. Okay, and that function is quite complicated, as you can see, 0.75 Prandtl to the power half divided by something blah 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 blah. So that's okay. You will have these correlations with you, no need to memorize. Only thing to remember is for a flat plate correlation in forced convection, Nusselt was proportional to Reynolds to the power half. And here it's proportional to Grashof to the power 1/4. Okay. Next, so this is the local Nusselt number at any x. If you want to find out if the height of the plate is capital L and you want to find out the average Nusselt number, then you have to find it out in this manner. Okay, h bar is 1 over L h del f h dx, and so you work it out and you will see that the Nusselt number, average Nusselt number, is 4/3 times the Nusselt number at the top, which is at x equal to L. For forced convection, we found it to be half, is 4/3. Okay. Clear? So similarly, in summary, we have like forced convection, we also have a correlation for natural convection for flow for natural convection from a vertical heated plate. Okay. Now what happens is if the Grashof number keeps increasing, what happens is because of what is called the amplification of these disturbances, what we have is something called flow instability. And as a result, the flow changes from laminar to turbulent. It is no longer going up in these layers, but instead it changes. Just let me get the laser pointer. It is no longer going up in layers like this, but however it changes and it kind of disperses. And that is when we transition from laminar flow to turbulent flow. Okay. At what distance from the leading edge, or at what value of x is this transition going to happen? Well, that x, or xc as we are calling it, x sub c, is going to correspond to this transition Rayleigh number of 10 to the power 9, which means if Rayleigh number is less than 10 to the power 9, it is laminar flow. If it is greater than 10 to the power 9, it is turbulent flow. Okay, so again, which correlation to use, when to use, this you have to determine before solving the problem, just like we did in forced convection. Clear? Just go through this slide once and make sure that you understand everything.
So again, remember here that the transition value of 10 to the power 9 is that of Rayleigh number, not Grashof number. Rayleigh number again is Grashof times Prandtl. Okay. Now, apart from this analytical solution, which is a little complicated, especially the function of Prandtl number, there are also some empirical correlations that people have developed. The first one is, or these correlations is by two gentlemen. I've forgotten to write their names here. Let me see if I can write it. Sorry, here I cannot change. Sorry. Okay, please make a note here. I will also do it. Its correlations are by Churchill and Chu. Churchill and Chu in 1975, they presented these correlations. The first one is for laminar flow for Rayleigh number less than 10 to the power 9. And you see that correlation. 0.68 plus 0.67 Rayleigh to the power 1/4 divided by something, blah, blah, blah. Okay. Turbulent flow is a similar correlation as you see below, 0.825 plus something Rayleigh to the power 1/6. Okay. Now these are average Nusselt numbers. Please keep that in mind. The ones that we saw before, this will give you your local Nusselt number as well. At any x, you can use this analytical correlation derived from analytical solutions to get a local Nusselt number. Whereas over here, this Churchill and Chu's empirical correlations is for the average value along the across the entire heated surface. Okay. Now note here, if you look at both these correlations, for laminar flow, Nusselt varies as Rayleigh to the power 1/4. And for turbulent flow, and that is not straightforward, but the dependence is Rayleigh to the power 1/3, because you see 1/6 inside, and then you outside the second bracket, you see a squared. Okay. So the last thing that I would like to tell you is what I've written here, that for turbulent flow, please note that this is average over the entire length. This is not like, separated initially by laminar, then followed by turbulent or anything. If it is turbulent flow, you can use it over the entire length to get the average Nusselt number or average heat transfer rate, average heat transfer coefficient. Any questions? So once again, you please note that these are again new tools that you are getting in your toolbox, these correlations. So most of the problems that we solve in convection, I've probably repeated this several times, I'll do it again. It's primarily correlation based. You have to understand the situation. And you have to use your judgment as to which correlation I have to use among all the ones that I have in my toolkit. Find out which is the most appropriate one and use it. Okay. I'll end the slideshow and come back to my, what's the time, 8:32. Fine, good. And come back to my OneNote, the handwritten notes. So refer to slides for vertical plate correlations. Okay. Now, two things I want to, or basic, or rather at this is one thing important. To calculate Nusselt number, never use this is wrong. Instead use H bar is 1 over L Hx dx, which essentially means okay. This is correct. This is wrong. Okay. We can do an example. I believe it will work here. Some cases it doesn't matter. It may lead you to the same solution, but that's not correct. Let us take this one, for example. Nusselt x is some function of Prandtl number times, as we found out, brush of x by 4 to the power 1/4. Okay. So now A, Nusselt L, by the first definition, which I said is incorrect, will be 0 to L Nusselt x dx. So 1 over L, you take Grashof that thing out, and okay. So 1 over L, Grashof, Prandtl, whatever, you even take this 1 by 4 to the power 1/4 out. You get G beta delta T. Sorry, I can probably take everything under this 4th. G beta delta T over 4 nu squared to the power 1/4. Take all that out, and what we have is x to the power 3 by 4 dx. Right? So what does it give me? X to the power 3/4. That integral 0 to L would be what? This will be 3 by 4 plus 1, which is 7 by 4, and L to the power 7 by 4. Right? So this 7 by 4, this L cancels out, it will again become 3 by 4. And what you will get is therefore 4 by 7 Nusselt L, isn't it? Okay, this is something we got. What was the other thing we said? This is Nusselt X. So Hx is going to be Nusselt X by this. So therefore, Grashof, Prandtl, all that stuff. Grashof x to the power 1/4 by 4. Not by 4, by x. And then 1/4 to the power 1/4. Whatever. So h bar, I said, is 1 over L, 0 to L, hx dx. Okay. So you go through this. Let me not spend more time on this one. Like before, Grashof will be g beta delta t over 4 mu squared to the power 1/4. And you have 0 to L. And you will have x to the power minus 1 by 4 dx. So let me take this whole thing out, and this becomes minus x to the power 3/4. So L to the power 3 by 4 divided by 3 by 4, which essentially becomes 4 by 3 times HL. Okay, and therefore Nusselt average is going to be okay. So as you can see, here we got 4/3 Nusselt, and here we got 4/7 Nusselt. Definitely 4/7 Nusselt is wrong, because the average cannot be lower than the least value. So this is wrong. Okay, and this is correct. So please keep that in mind. Many people make this mistake. See, Nusselt is just a non-dimensional term. It's not a physical quantity. H bar, heat transfer coefficient, on the other hand, is a physical parameter. Okay, is physics based. Comes directly from the rate of heat transfer. Nusselt, on the other hand, we have taken a physical parameter, multiplied by something, divided by something to get a. Okay. Of course, it has its own significance, as we said earlier while we were discussing forced convection, that it is kind of a non-dimensional temperature gradient at the wall. Okay, but please keep in mind, this is very important to note, that when you have an expression for local Nusselt number and you want to find an average over a certain length, never integrate the local Nusselt number. Convert it to local heat transfer coefficient first, find out the average heat transfer coefficient, and then define Nusselt number, average Nusselt number. Okay, all right, that's a small anecdote. Let's come over here and talk about what happens for a vertical cold plate. (840). See, if the plate is cold, which means it is at a lower temperature. So this is TW, and let us say this is T infinity, and TW is less than T infinity. Of course, this is gravity again. Then what happens is, just by the same logic, my temperature is going to reduce from T infinity over here to TW over here. Okay. So therefore, what happens next to the cold wall? My air becomes colder, it becomes heavier, and it will try to sink. So I will have, of course, zero velocity at the wall, but then as I move away in the y direction, I'm going to see a downward velocity component in the x direction, in the y direction. See, in the x direction, sorry. So therefore, my velocity gradient will be, এই আস্তে কথা বলো, কি হচ্ছে? বন্ধ করো এটা। So the velocity will have a downward component of velocity, which again, like before, is, oh, sorry. Okay, they will drawing skills are not great. Okay, they will all both come to 0 at the. All right, so this is how it is going to be. So this will be my u variation. Okay, so these are sometimes very favorite questions in vivas and interviews, because they know that in a standard lecture you will be taught a vertical plate facing upwards, heated vertical plate, and then what the interviewers try to see is, can you use your thought process to come up with this solution using the same logic. Okay, another very favorite question is, we have in forced convection, we have said I have a stationary plate and there is a fluid flowing over it. Now what they will say, what if it's a different, what if it is different? Let's say I have a quiescent room, and then I take a horizontal plate which is moving at a certain velocity. So then how would the boundary layer look like? How would the temperature profile look like? And not temperature profile so much, how will the boundary layer look like? Okay, so but if you know that exactly how did we derive, or how did we come up, what was the logic behind coming up with these profiles, you will be able to derive the velocity temperature profiles for those scenarios as well. Okay, okay, let us get to a problem. Very simple one. We have about 15 minutes left, the first hour. This very simple problem. It's consider a flat plate. Okay, 0.5 meters by 1 meter. Held vertically and maintained at 100 degrees C. Air is at 40 degrees C and 1 atmosphere. Okay, so the first thing is, calculate H bar and total heat transfer. And B, calculate heat transfer by radiation exchange. Okay. Now, there is a reason why I have given this problem. There are the two reasons. Okay. Now, the first thing is it says that this is a vertical plate of dimensions 0.5 meters by 1 meter. Okay. But I have not told you that in which direction or what is the direction of this 1 meter and 0.5 meters. In other words, I have not told you that in the vertical direction, is it 0.5 meters or is it 1 meter? If this is gravity, is my plate like this? Or is my plate like this? So I have not told that, so you can assume, you can make your own assumptions. But let me ask you that if you were a designer and this problem was not, and your goal is to find out, or your goal is to maximize heat transfer, which one will you go for?
The second one,
The second one. Why?
there is a chance the flow can be turbulent there.
Very good. Very good. Okay. That's very nice. The flow can lead to or can transition to turbulence, and in which case my heat transfer coefficient will go up. My average heat transfer coefficient will also go up. Absolutely. That is one case. Okay. Now let us say, but however, let us say that given all the other conditions, the delta T is known, etc., you find out the Rayleigh number for the first case and for the second case, and you find out that in either case, we will stay within laminar flow. Okay. In such a case, what would you do? So does the heat transfer coefficient, what happens to the heat transfer coefficient with respect to height? Come on, I think I'm expecting an answer here. So friends, this is where I think the concepts have to be internalized. Okay. As we go up from the bottom edge, as we go up, the boundary layer thickness increases. If the boundary layer thickness increases, it means the heat transfer coefficient is lower. Okay. So therefore, the heat transfer coefficient, assuming it's laminar, is going to be lower for at the top edge for the 1 meter for the second case than at the first case. And therefore, the average heat transfer coefficient as well is going to be higher for case 1. Okay. If flow remains laminar throughout, H bar L, or H bar rather, for case 1 will be higher than H bar for case 2. However, situation may change if flow turns into turbulent in case 2 and remains laminar in case 1. Okay. All right. So let us consider case 1. So in that case, the calculate rush of L. So from there you calculate Nusselt-L. So from there calculate Rayleigh-L. Calculate check laminar turbulent. Then calculate Nusselt-L. Okay. So from there calculate H bar. And finally, Q of natural convection will be H bar times the total area, because you have two surfaces, remember, both sides, times delta T, whatever you get. Okay. So my solution, what I have worked out is 128 watts. Okay, you need to get all the fluid properties, etc., etc. 128 watts. Okay. Now case B, this is the second point I wanted to make, was the radiation effect. Okay. Now your epsilon has not been given to you. So assume epsilon equals to 1 or 0.5, whatever you want to. Let me take 0.5. Now, what is this case? This is a vertical plate completely exposed to air, which is like an infinite medium. So therefore, the shape factor from the surface to wherever it is exchanging heat is 1. Okay. So therefore, all those conditions, F1 to 2 is 1, F2 to 1 is not equal to 1. So those are all valid. So my Q radiation will be sigma epsilon, again A total, T wall to the power 4 minus T infinity to the power 4. Okay. If you do this, according to my, well, actually I worked out with epsilon equal to 1, so this will be just half of that. I'm getting about 138. Okay. So therefore, note that Q radiation is greater than Q natural convection. Okay. If I had taken 1, then it would have been greater than twice natural convection. So which means that radiation can have a significant impact under natural convection conditions and should not be ignored. Okay. If we neglect radiation, we are going to basically underestimate heat transfer by a large extent, and that would be stupidity. If you as an engineer, your aim is to improve heat transfer. Okay. So therefore, please keep in mind that you should not be neglecting radiation, because for forced convection, yes, forced convection, probably your total heat transfer would have come out to be whatever 5 times or 10 times 120, maybe one close to a kilowatt or 900 watts. In that case, okay, if I neglect 138, it still should not be, but okay, it will be a small fraction. But here the error will be large. Okay. So sometimes in forced convection, even if we neglect, we say that okay, well, it's a little conservative, fine, and if I can dissipate X amount of heat just by forced convection, in reality, I will probably be able to dissipate even more. But in natural convection, I mean, that kind of a factor of safety is stupidity, because you'll end up over designing your surface area, which is not required. Okay. All right. So let us take a break here. Let me stop the recording. And when we come back, we'll finish off natural convection and do a few more problems. Okay. If time permits. See you in 5 minutes.